In this video, we're going to take a high-level overview of the architecture of Hadoop. Essentially, we're going to look at the two pillars upon which Hadoop is built. The HDFS side, or Hadoop Distributed File System, provides the storage, and the MapReduce side provides the processing. We'll look at the software architecture, including specific daemons, and we'll also investigate Hadoop's value propositions. These two pillars that I'm talking about, storage and processing, are represented in this diagram that we see throughout this course. The storage side provides HDFS. Think of it as a distributed, redundant file system. In the HDFS chapters, we talk in more detail about these. The processing side is provided by the MapReduce daemons, or the green parts of this diagram. Think of this as being a distributed processing system. Each of these pillars requires several long-running daemons on the master and slave side. Just remember that the raw storage and processing occurs on the slaves, and the coordination and delegation occurs on the masters. Before we dig into more details about this chapter, let's get several definitions out of the way. First up, a job. A job is all the tasks which need to run on all the data. This includes the MapReduce code, as well as the HDFS data inputs that we're going to analyze. A task is a single piece of individual analysis, either a map task or a reduce task that occurs on a subset of the data. Slave and master nodes are physical machines. This is very easy to confuse with these name nodes and data nodes. Just realize that the name node and data node are the individual JVM daemons that run on those physical machines. We also use several abbreviations here. The NN is the name node, the JT is the job tracker, and the 2NN is what I'm going to refer to as the secondary name node. These are all the master daemons that you see in the upper part of that diagram. The DN is the data node, and the TT is the task tracker. In a typical Hadoop cluster, you'll have one data node and one task tracker per single individual slave. As a quick aside, let's talk about the different versions of MapReduce. There's also a MapReduce version 2, but it's not ready for prime time yet. In this course, we're going to talk specifically about MapReduce version 1. It uses its own daemons, the job tracker and the task tracker. MapReduce version 2 is coming for general release, and I think it'll probably be out in Q1 or Q2 of 2014. It should allow for processing to scale better. It also provides a bit more dynamic allocation of resources for processing. Again, because MapReduce version 1 is the only stable release available, we won't discuss MapReduce version 2 in this course unless otherwise noted. So a Hadoop cluster is again both storage and processing via master and slave nodes. It involves 5 long-running daemons. There are daemons that run the storage piece, which is the name node. It's a master daemon. The secondary name node is also a master daemon, and the data node, which again exists one per slave. On the processing side, we have a job tracker, which is the master daemon, and task trackers, which are the slaves. Every time you see this diagram, just remember the blue parts are HDFS and the green parts are MapReduce. The core Hadoop software again involves several long-running daemons. These 5 daemons need to be up and running at all times. The master daemons you want to think of like a good boss. They do orchestration, they do coordination, and delegation, and then they conveniently get the hell out of the way. Slave daemons do all of the work, which is storage and processing. The raw blocks comprising the input and output data, as well as the actual processing work itself, are always done on the slaves, never on the masters. Zooming in on the master daemons, we have a name node. This handles all of the storage metadata. It keeps all that metadata in volatile memory for fast lookup, but it also persists the data to disk. The secondary name node is perhaps the most unfortunately named piece of software ever. It simply performs a checkpointing function only for the name node. It is not a warm, hot, or any kind of standby mechanism at all. It also uses as much memory as the name node. The job tracker master daemon coordinates all the processing of the stored data. It also handles the scheduling of the job processing. A typical cluster will only have one each of the name node, the secondary name node, and the job tracker. Again, all of this is discussed in more detail in the relevant chapter. When placing the master daemons, it's highly recommended that we use separate hardware for the name node and the secondary name node. This is because a catastrophic hardware failure on the name node is possible, and we want to be able to quickly rebuild the secondary name node as the name node. That secondary machine is going to need as much RAM as the name node anyways, So if you simply buy a second machine, you get all the flexibility of having redundant hardware, just in case you have that single failure on the name node machine. At some point later in the future, you might need to move your job tracker out to its own piece of hardware as the cluster grows. Most clusters simply deploy the name node and the job tracker on that one single machine, leaving the secondary name node on a separate physical machine. Zooming in on the slave daemons, on each slave we will have a data node, which handles the raw data storage reads and writes. In Hadoop, we no longer have a central data store, as we saw with the SETI at Home project in another chapter. Processing tasks are handled by a long-running daemon called the task tracker, which handles individual task assignment operations on a single piece of data. Each of these slave daemons, on a short-term basis, typically just a few seconds, heartbeat and report into the master daemons. These heartbeats and reports consist of messages like, hey, I'm alive and I'm here. Here's what I'm storing for the data node. I can take tasks for the task tracker. I'm still working on tasks at the task tracker. Or hey, I finished tasks on the task tracker. Hadoop has several failsafes baked into it. The master and slave daemons are able to coordinate, recognize, and automatically repair failed data writes and reads, under or over replication of data, failed tasks, failed hardware, such as bad disks, bad NICs, and so forth, failed Hadoop software on the slaves, such as a data node or a task tracker being stopped, and failed network connections to the slaves. Hadoop can automatically repair all of these situations without any manual user intervention. As mentioned in other chapters, Hadoop has several value propositions. First up is the costs. Open source software running on commodity hardware is incredibly cheap. It's very easy to deploy and maintain Hadoop, and using the right tools, you can get up and running with Hadoop in as fast as 15 minutes. It has very dependable, horizontal, linear scale. Every slave that I bring to the cluster gives me some percentage more capacity. For example, in our 6 slave node cluster that we have right here, if we had 6 additional slave nodes, we would double our capacity for both storage and processing. Clusters in Hadoop can grow very, very large to be able to store petabytes of data and process thousands of tasks simultaneously. Hadoop is relatively quick. Again, it provides parallel processing via MapReduce. It has several failsafes baked in, including redundancy and fault tolerance, as well as self-healing. In this chapter, we took a high-level overview of the pillars of Hadoop, the HDFS or storage side, and the MapReduce or processing side, which are enabled via 5 daemons. We took a quick overview of the software architecture, which is covered in more details in the relevant chapters, and we took a quick overview of Hadoop's value propositions.